Okay, so now we bridge from grade 11 trigonometry to grade 12 trigonometry, and we'll start by talking about our special triangles. So you may remember this image from grade 11 that helps us identify what those special triangles are. We have two of them that we look at. So here is a square, and I know it's a square because of the little tick marks on each side that tell me that these are all the same length, and they're a length of 1. So the challenge that I'm giving is, without using a protractor or ruler, to find the values for all the sides and interior angles of each of these shapes. So we'll start here with this one. So when we look at this, we can see that, of course, this would be a length of 1, and then this would be a length of 1, which means that if we wanted to find the third side, we could use Pythagorean theorem. Pythagorean theorem says square one side and add to the square of the other side, and that will give you the square of the longest side, which is c squared. Of course, in our scenario, well, whatever, I'll call it c squared still. So 1 squared is 1, 1 squared is 1, so this is 1 plus 1, which is 2, and then we square root it to find the value of c instead of getting c squared, so we can see that the third side of that triangle is the square root of 2. Now, the next thing is to look at the angles. So we can see these little boxes in the corners. These tell us that we have right angles. In grade 11, we would have called those 90-degree angles, but in grade 12, we call them pi by 2, because in the Cartesian plane, we know that if we go all the way around the circle, that's 2 pi radians. If we go halfway around the circle, that's 1 pi radian. And so if we're only going from here to here, so a quarter of the circle, that is pi by 2, okay? Because it's half of pi, it's half of the top half of that Cartesian plane. It's a quarter of all the way around, and 1/2 is a quarter of 2. So this angle is pi by 2 down here. Now, the other two angles that we have on the side here, we can see that they are part of those original right angle corners that have now been cut in half because we have the diagonal going directly across, and because it's a square, it cuts it in half exactly. So this angle is half of pi by 2, which would be pi by 4. So that means that this angle up here is the same thing. It's also pi by 4. So in grade 11, yes, you would have called this 45 degrees, you would have called this 45 degrees, and you would have called this 90 degrees. But now that we're in grade 12, we're not going to use that language anymore. We're going to work in radians, and we're going to try to think in radians whenever possible. So I'm not going to keep going back and forth between degrees and radians. I'm just always going to try to voice to you my thoughts in radians in order to encourage you to do the same. So it's the same special triangle from grade 11, nothing new. It's just that we're using radians to measure those angles instead of using degrees. And just to look at that on the Cartesian plane, that angle that goes halfway from between 0 and 2, or 0 and pi by 2, would be pi by 4, like this. And that makes sense as well, because we can see, okay, 1 pi by 4 is here, 2 pi by 4s, 3 pi by 4s would take me here, and then 4 pi by 4s would be a full pi, right? So you're basically just taking pi and cutting it up into 4 pieces. That's what we've got there. Our other special triangle comes from an equilateral triangle, and we know it's equilateral by this diagram because we have the tick marks on each of those sides, and the special triangle that we're kind of focused on is that shaded part, just like what we had in the other triangle. So because this is 2, 2, 2 around the outside, we know that this length is 2 as well, and because this is an equilateral triangle with this this length that's going straight down and making a right angle with that bottom side there, we know that that's cutting this side exactly in half. So we know that this length is 1. Now, similarly, we can use Pythagorean theorem to be able to find the length of that missing side, that vertical side that's in our triangle here. And so we fill everything in. 2 squared is equal to 1 squared plus b squared. Rearrange, so we have 4 minus 1 is equal to b, and then we square root both, or it would be equal to b squared, so we square root. So this is the square root of 3 is equal to b. So this is, again, the same special triangle that you remember from grade 11. Now we're going to think about what its angles would be in radians. So we know that all of the angles in a triangle add up to 180 degrees is what we thought of previously, but now we are going to be thinking of that as we know that 180 degrees is the same thing as pi radians. So we are taking pi radians and dividing it into 3 to find this angle right here. So pi divided by 3 is pi by 3. Now we know that by cutting this triangle in half by dropping that side down, this pi by 3 angle got cut in half as well. So pi by 3 divided by 2 is pi by 6. Some people really struggle with that idea that pi by 6 is a smaller angle than pi by 3, forgetting that when the denominator is bigger, the value of the fraction is smaller, but you will get used to it. You just have to keep at it. And then, of course, we have that our right angle down here is pi by 2 radians. So again, looking at these special triangles, they're exactly the same as they were in grade 11. It's just that now we are talking about them as being in radians. So just real quick, I'm going to draw like a different orientation because some people struggle to get the special triangles when we, turn them a different way. So in our special triangle where we have two of the sides, the two shorter sides being the same length, then this is length 1, this is length 1, and then the hypotenuse is length root 2. Then we have a pi by 2 angle in that right angle space, and then each of these other angles is pi by 4. When we're talking about the other triangle that comes from our equilateral triangle, we get that the longest side here, like the hypotenuse side, is 2 because it comes from that equilateral triangle, which would be like this. And then that other side there is a 1. And then the one that goes straight down is a root 3. We know that the bigger angle is pi by 3 and that the smaller angle is pi by 6. There aren't a lot of things in general that I feel like I encourage my students to memorize. But the special triangles are among those few things, okay? So you definitely want to be comfortable drawing the special triangles in any orientation, around your page. It shouldn't have to only be one way. Don't memorize, oh, the 2 is next to the 3 or whatever. Don't do that. Instead, every time you think of the special triangles, just think of the shapes that they came from, the square and the equilateral triangle, and then label all the sides and angles based on that. Okay, so why bother with all these exact values? Well, actually, exact values are what radians are so great for. This is when you get to advanced mathematics, you'll really only be working in radians. You'll rarely be working in degrees. That was my experience anyway. The beauty of the special triangle is it helps us to, again, maintain that exactness whenever possible. So determine the exact value for each ratio. For each of these, I'm going to draw the angle. Whenever I'm given this kind of instruction, I'm almost always, whenever I can, I'm going to start with drawing the angle, okay? That helps me get an idea of what I'm actually looking at, and then I can consider the ratio and kind of go from there. So sine of pi by 2, the first thing I'm going to do is I'm going to draw what pi by 2 looks like. I know that pi by 2 is half of pi, so this would be here. So pi by 2 is that right angle that goes there. Now, it's asking me about the sine value of that, and we know that sine is y over r. So what we're going to do is we're going to look at if we were somewhere along this terminal arm, because this is our terminal arm here, then what would be the value for any point on there? It doesn't matter which one you choose. What would be the y value? What would be the r value? It's convenient to always choose that the radius is a length of 1. We just like to do that because it's nice whenever we have a choice. So that means that if this point is somewhere on that line, then the x value would be a 0, and the y value would also be a 1 because it's traveling from to get to this point up here, we have from 0 up to a value of 1 because this length is 1 from the radius, okay? So it's just convenient to choose that. So I can do a quick little jot for myself. I have x, y, and r. These are the ingredients that I might need for any trig ratio. Because we have sine, we only really care about the y and the r. So the y value is 1 and the r value is 1. So sine of pi by 2 is 1. And when we look at the graphs of sine, cos, and tan, you'll remember that sine of pi by 2 is 1 once you get familiar with the fact that pi by 2 is the same thing as 90 degrees. Okay, next example. So again, I always start by drawing my angle. So 3 pi by 2 means that if this is pi over here, which it is, then this is 1 pi by 2, 2 pi by 2s, and 3 pi by 2's right here. So this must be the angle right down here, 3 pi by 2, okay? And we know that this is pi by 2 because it's half of pi, okay? So we just need 3 kind of chunks that size. So there's my angle, 3 pi by 2. I'm going to put my coordinates somewhere on that terminal arm. It doesn't matter where. I'm going to conveniently choose my radius to be a value of 1 because I can, because it's not given to me, so I might as well choose it. And that is a 1 there. So again, I'm going to say, okay, what's x, what's y, and what's r? I only really need 2 of these, but, oh, and I actually didn't fill it in the last one. In the last one, we knew that x was 0, so I can plug that in. So now over here for this point, again, x is 0 because we're on the y-axis like this. The y value is 1 because the radius is 1, taking me to that point. So now I need to consider, okay, with cotangent, what are the 2 pieces that I need? Well, we know that cotangent is the reciprocal of tan. We know that tan is y over x. So that means cotangent must be x over y. So this, in this case, would be 0 and 1 together. So this is equal to 0 over 1, which is 0. Okay, so notice that I haven't pulled out my calculator at all for any of these exact value questions. I'm just looking at the angle, the value of x, y, and r. I don't need my calculator to tell me these values. Okay, now next one is secant of 2 pi by 3. Again, I start by drawing that angle, 2 pi by 3. Where is that? Well, I know that this is pi right here, so pi by 3's means that I'm cutting that pi into 3 equal pieces. This is like 1, 2, 3. That would be the idea there. So I want 2 of them, though. It says 2 pi by 3's. So that means I need to go 1 pi by 3, 2 pi by 3's. So my angle is over here. This is 2 pi by 3. It ends at this terminal arm right here, like that. So now what I need to do is just like before, I put a point somewhere on that terminal arm. Now we need to consider what are the x and y values that I need here, and r values as well. Okay, so here comes in some of that terminology that we discussed. Because the principal angle here is 2 pi by 3, I know that this related acute angle is 1 pi by 3. This is pi by 3 down here. And I can see that this this arm that I've drawn down, this black arm from the point, is pi by 2 because it's a right angle. So that means that I have 3 angles that need to add up to pi. So we have pi by 2 plus pi by 3 plus some other angle needs to give me a total of pi. So a half plus a third plus something is equal to pi. What is that? You'll get more comfortable over time remembering that it's pi by 6. Okay, we know that this missing value in here is pi by 6. In grade 11, you would have memorized that this pi by 3 was 60 degrees, and that this was 30 degrees, and that this was 90 degrees, which together would add up to 180 degrees. But again, we are living in the world of radians. So we have pi by 3, pi by 6, and pi by 2. Okay, so now I hope that this jumps out at you as, aha, this is my special triangle. I know that this comes from this equilateral triangle that would look like this, where this side would be 2, this side would be 2, and this side would be 2. But we only really care about the right angle triangle that's created from that equilateral triangle. So I don't so much care about that 2 over here, and I don't so much care about this 2 down here, except to figure out that that means that this length would be a 1. And then we know that that third side is root 3. We could find it with Pythagorean theorem, but this hopefully you can commit to memory. Okay, so here's my beautiful special triangle that I've drawn now in the Cartesian plane. Now the next thing is to consider about the sign. So x, y, and r, each of these has a value for this angle over here. Now the radius is always positive, so that's just a straight positive 2. And in this quadrant, because this is going upwards, my y value is the square root of 3, just positive. And because we are going left on the x-axis here, my x value is a negative 1. So now that I have my 3 values for x, y, and r, I can consider what do I need to know for secant. Well, we know secant is the reciprocal function of cos theta. We know that cos is x over r, so that means that secant must be r over x. So in this particular case, that r is a 2, and that x is a negative 1. So the exact value of secant of 2 pi by 3 is negative 2. All right, next one, cos of 5 pi by 4. So here we have pi is halfway across the circle. So if I cut that pi into 4 pieces like this, 1, 2, 3, 4, then each of these pieces is pi by 4, right? So I need 5 of those pieces though, so that means I need one more guy over here. So that means that 5 pi by 4 is down here in this quadrant. This is my angle 5 pi by 4. So there it is, that principal angle 5 pi by 4. So now, again, like before, I'm going to create this kind of right angle triangle here, and then I'm going to look at what my related acute angle is. So we know that because I needed one more pi by 4 to get to that 5 pi by 4, this angle is pi by 4 here. That's my related acute angle there, okay? And then we know that this is also pi by 4 because this is pi by 2, which is a right angle, and those 3 angles together, pi by 2 plus pi by 4 plus pi by 4, is a total of pi. And we know that triangles have a total of pi radians, just like in degrees, they would have a total of 180 degrees. So again, this is one of our special triangles. So we know that the two perpendicular sides are 1 and 1, and then the longest side is our square root of 2. Now the next thing is to consider about the sign. So because we are on the left side of the y-axis here, then we are in the negative x zone. And because we are on the bottom half of our Cartesian plane here, we know the y value is negative here as well. We know that the radius is always positive. So we have x, we have y, we have r. Our x and y are both negative 1, and our radius is the square root of 2. So now we go back up to the question. Cos of 5 pi by 4, what do we need to know to be able to do that? We know that cos is x over r, so these are the values that we need to look at. So x is a negative 1, r is a root 2, so cos of 5 pi by 4 is negative 1 over root 2. And we're done. This is a nice exact value, but if you remember from grade 11, we often like to rationalize the denominator. We don't like having a radical in the denominator, so we would do that by multiplying the top and the bottom by that square root 2 to get rid of it. And this would then be equal to negative root 2 in the numerator, and then root 2 times root 2 is positive 2 in the denominator. So this is the exact value of cos of 5 pi by 4. The nice thing is that if you type cos of 5 pi by 4 into your calculator in radian mode, then it won't give you this nice answer unless you have one of those really nice calculators that does. But we're able to identify that exact value in this way. Okay, last example like this. Cos of 11 pi by 6. So again, I start the same way. I draw the angle first. So pi by 6 means if this was pi here, that means I'm cutting pi up into 6 pieces. So that means 3 pieces on this side, 3 pieces on this side, and they're all equal amounts. Okay, so if I take all of these, that's only 6 pi by 6s. I need 5 more. So that means I need to cut these guys into 3s as well, so that this second batch of pi I can split up into 6 pieces as well. So we need, we had 1, 2, 3, 4, 5, 6 around the top. Now we need 7, 8, 9, 10, 11 pi by 6. So 11 pi by 6 is over here, this big, huge angle. So there's my 11 pi by 6. And we can see that 11 pi by 6 is almost all the way to 2 pi right here, which means that this piece that's left over, this little remaining piece, our related acute angle, is 1 pi by 6. So together, 11 pi by 6 and 1 pi by 6 would give me 12 pi by 6. So, and we know that 12 pi by 6 is the same thing as 2 pi. Okay, so that means our related acute angle is pi by 6, so we can fill in the rest of our triangle as well. We know that because this is pi by 6 and this is pi by 2, which is a right angle, that this one must be pi by 3. And we're happy because that's one of our special triangles. So we add in the side lengths that we know for those special triangles. Again, this comes from that equilateral triangle where the 3 equal angles would be pi by 3. So that means that this side is length 2, this side is length 1, and this side would be the length of root 3. But now that we're in the Cartesian plane, we're not really talking about lengths, we're talking about values of x and y. So x and y and r, what are those values? So because we're in the bottom right-hand corner here, the y values are negative because we're going down, and the x value is positive because we're going right. So we have positive root 3 for x, negative 1 for y, and the radius is always positive. It's positive 2. So now I go back up to the top and think, okay, well, what do I need to know for cosecant? We know cosecant is the inverse of sine. We know sine is y over r. So that means that cosecant must be r over y, just the reciprocal of that. So in our case, that's a 2 over a negative 1, which is a negative 2. that's how you find the exact value using special triangles and radians. It's exactly the same as what you did in grade 11. It's just that now we're living in the radian world. Okay, next type of question. Now, sometimes we are given problems where we don't know what the angle is, and we're being asked to find the angle, and we have to keep in mind there are multiple answers for any of our questions that look like this. So to start a question like this, so where it's asking us to solve for that angle theta, where tan theta is equal to negative 7 over 24, I'm always going to start by drawing. So I'll draw what I can here. I don't know what that angle is, but I do have some information with this 7 and the 24. We know that tan is equal to y over x. So that means that this information is telling me one of two possibilities. So the idea here is maybe it's telling me that the y value is negative 7 and the x value is positive 24, right? That would give me a y over x of negative 7 over 24, right? Or maybe it's telling me that the y value is positive 7 and the x value is negative 24. Like maybe the negative is down there with the x value. These are like my two ideas. So that means that I need to draw these two different possibilities. So if I draw the first possibility where y is negative 7 and x is positive 24, then that means that I need to go down by 7 and then right by 24. So that would put me over here. And my terminal arm would go to the origin from that point. If the other scenario that we're looking at is that y is positive 7 and x is negative 24, then that means I would need to go up by 7 and then left by 24, because up would be positive for y and left would be negative for x. So then I'd have my point over here, and again I would connect that point to my origin because the angle is always close to the origin. So the next thing I just want to kind of swing back to is this idea of the cast rule here. So we can see that tan is a negative value overall. So does it make sense that the two terminal arms that I drew, are they in the right space? So down here in this quadrant, this would be C, A, S, T. So that tells me that cos is the only one positive in this quadrant and sine is the only one positive in this quadrant, which means I must be correct because tan would be negative here then, and tan would be negative here then as well. So I've drawn my two terminal arms in the two quadrants where they definitely belong. Cast rule kind of emphasizes what I know, but really cast rule is just capturing this idea behind x and y having sine in the Cartesian plane. Okay, so let's look at that first possible angle that we have from our initial arm to our first terminal arm that's there. So we can see that this angle theta, this is one possibility for theta. We have another possibility for theta that goes to that other terminal arm here. We actually have an infinite number of possibilities for angles that go to these two terminal arms, but because we're given this domain restriction that says stay within one circle, do not go beyond one circle, and do not go in the negative direction, then we really only have these two answers, okay? Whenever you're given a restriction like that, just between 0 and 2 pi, you're always going to have two answers. Actually, not always, almost always. There's a couple of exceptions to that. Okay, so now to figure this out, we need to use our calculators because these are not, the 7 and the 24, they're not any of our side lengths from our familiar special triangles, so we need our calculator to help us. So we remember what we learned from grade 10 when we're solving for theta with trig equations like this. We can take the tan inverse of both sides. So on the left side, tan inverse of tan cancels out the tan, leaving us with just theta. Then we have tan inverse that we have to do on the other side. It's very important that you keep the sign with you when you do these problems, or else your calculator will give you something else. It's also very important to make sure that your calculator is in radian mode. Okay? Every calculator is different in terms of how you change what mode it's in. Just make sure that you are in radian mode when you do this. So when I do that, I get theta is negative 0.284. Let's stop there. Okay, and that's approximate. So this is one value of theta. So I have to consider, is this theta 1 or is this theta 2? Well, it's giving me this negative 0.284 degree, or 0.284 radians. So I have to think, well, how big is 0.284 and where is it taking me? So if you remember from the last topic that we learned about how big a radian is, 1 radian is a little bit less than 60 degrees. So it's just this kind of acute angle like this. So this is 1. So anything smaller than that is going to be smaller than what you have in your mind as 60 degrees. So we have an acute angle that's negative. So that means we must be going down in this direction and not by too much, okay? So this tells me that this must be theta 2 because that ends up in that area that we see here. So this is theta 2, or that's the terminal arm for theta 2. However, it's not really theta 2 because theta 2 is a positive angle because of our domain restrictions. So because we can only have positive values for theta 2, we need to change to figure out what this value actually is that we can include in our solution set, since our solution set says that we can't use negative values for theta. So we have to use the fact that this is giving us our related acute angle. It's giving us this angle in here. So this is actually beta. This is what this is giving us. But because it has a sign, we always consider beta to be a positive angle. Similarly, how we think of the radius as always being a positive, because beta is just like the smallest angle that gets the terminal arm to the x-axis in any direction, can be anywhere. It doesn't really have to start at the initial arm like all the other kinds of angles do. So it's a little bit special. So our related acute is 0.284 radians. So if we want to figure out what theta 2 is, then theta 2 is going to be that full circle, like this full circle except this last little bit, right? We don't want to include that last bit in it. So that means that we have to take the full circle, which is 2 pi, and subtract our related acute angle from it. So again, we can use our calculator for that. We type 2 pi minus 0.284 into our calculator, and it gives us 5.999, which I'm going to say is approximately 6 radians. Okay, so theta 2 is 6 radians. We have one of our answers. Now we're wondering, what's this other answer? What is this other value that would take us from the initial arm to our other terminal arm? What is that theta? Well, we know that we have the same related acute angle. That beta here is the same as this beta in this space, okay? So this is also 0.284 radians. So now we have to consider how much is this angle that goes only, like just that highlighted part in purple, so from the initial arm to that terminal arm. So we're going to set up a similar kind of equation. We know that theta 1 then would be all the way to pi except for that last little related acute angle. So that must be pi minus 0.284. And again, we go to our calculators for that. And our calculator in radian mode gives us this value, 2.858 radians, approximately. So I need to put that little dot above. So this is my other value for theta. So again, before I move on, I just want to make sure that I did that right. I need to think it out. I always, always, always need to end by thinking it out. So is that a reasonable answer for this angle? Well, again, I have to think about how big 1 radian is. I know 1 radian is a little bit less than that pi by 3 angle, that little just shy of 60 degrees. So I know that I could fit a little more than 3 of them in the span of pi, right? Because they're a little bit smaller than that 60 degree size. So that's like roughly what 3 radians looks like. So I know that our angle should be 2.858, so it's pretty close to that. So it's somewhere here. So it's like in that quadrant on that side, and that matches what we saw when we drew a pretty rough sketch of what that angle should look like based on the fact that the two lengths of the x and y, or those two coordinates x and y, were 7 and 24. So we have our 2 answers. This is our final answer here. So therefore, theta 1 would be approximately 2.858 radians, and theta 2 would be approximately 6 radians. Now, officially radians don't have units, like the units cancel, so whenever you see an angle written without units, it's considered to be radians. All right, last one like that, very similar, but you can see that this time we have a different kind of restriction on our domain. So that means that we are going to have different kinds of answers. We're going to have more of them in this case. So let's talk about that domain restriction first. So negative 2 pi to positive 2 pi. So from 0 to 2 pi is here, right? To go from 0 radians up to 2 pi radians, that would be there. But by including from 0 down to negative 2 pi degrees, or sorry, negative 2 pi radians, then we have that amount there. So basically what's happening is we have going positive once around and going negative once around. So that means that we're going to end up with 4 solutions, because wherever our 2 terminal arms are, we're going to have 2 solutions in each of those quadrants, right? Okay, the positive trip around and the negative trip around. So again, I start by drawing a diagram. So cos of theta is negative 3 over 5. I know that cos is x over r. So that means that the x value, so like one possible interpretation of this is that the x value is negative 3 and the radius is positive 5. Or the other possible interpretation is that the x is positive 3 and the radius is negative 5. But hang on, we know that the radius is never negative. Okay, so that second possibility is not really there. This is our only possibility that we have. So x has to be negative 3 and the radius has to be 5. So let's draw what that could look like. Well, if x is negative 3, that means I'm traveling left from the origin by 3 units. And if the radius is 5, then that means I'm traveling to the point directly from the origin at a distance of 5. So this is the part where I get 2 answers, because it could be that the radius goes up here to be a length of 5, right? And then my point is at the end of this. So we can see that this is a negative 3 going in that direction and a positive 5 going up there, leaving the y value to be a positive. Or maybe the radius goes down here and is a length of 5. So that's still, possible. It would just mean that I get a different y value, and that y value would be negative in this scenario. So I have 2 terminal arms, just like I would expect to have. Now I need to consider all the different possibilities for theta. So just like in grade 10, I start with my equation cos theta equals negative 3 over 5, and I start to rearrange to solve for theta. And then I go to my trusty calculator, because 3 and 5 are not lengths that I recognize from my special triangles, and so I use my calculators to evaluate it, making sure that my calculator is in radian mode. And my calculator gives me this approximate answer of 2.214 radians. So now I need to ask myself, is that this guy or is that this guy? Which angle is my calculator giving me? Well, it's giving me positive angle, like a positive angle, so this is good. It makes my life like a little bit easier to start with, and it's a little bit more than 2 radians. So I have to think, where should that be? Well, we know that pi is a little bit more than 3 radians, so this has to be less than pi, and pi is here, so that means that this must be this angle right here. So theta 1 is approximately 2.214 radians. Okay, so we have one of our answers. That's really awesome. Now next, we need to figure out what our related acute angle is, because the related acute angle is this angle here, and it's also this angle here. So I can either find what that related acute angle is and add it to theta 1 twice, or I can add it just once to the amount of pi. So to find that related acute, so beta is our related acute, that's going to be pi minus theta 1, like that, which is pi minus 2.214 radians, and it's approximate, so I put that little dot above. So my related acute is 0.927-ish. And I'm keeping the full number in my calculator. I'm not stopping to reset. So that means that I'm trying to avoid rounding until I absolutely have to. So if the related acute is 0.927 radians, then that means to find theta 2, I need to add that to pi, like this. Theta 2 equals pi plus beta, which is approximately pi plus 0.927, which is approximately 4.069 radians. So again, I do a mental check to decide, is that reasonable for what theta 2 could be, just to make sure that I'm on the right track. So I think that this is my answer, that theta 2 is 4.069 degrees radians, but I need to look at my graph to decide. So I can see 4 radians would be, like I know that pi is a little more than 3 radians, because all the way around is a little bit more than 6. So it makes sense that just a little bit more than 4 radians would be just after that in this next quadrant down here. So we feel pretty good about that. We feel like that probably is that angle right there. And to be clear, that angle goes all the way from our initial arm to our terminal arm. This is that angle theta 2 that does that. So now we consider our domain restrictions. So our domain restrictions say that we can actually go back into the negative values as well. So that means that we have 2 more values for theta. So one of them is here, going to the nearest terminal arm in the negative direction, and then one of them is here, going to the other terminal arm in the negative direction. So again, I'm going to use my related acute in both of those scenarios. So theta 3, that first one that I drew, let's go this one right here, theta 3, we can see that that's, if we were to go negative pi, we'd go all the way, but we're just related acute angle shy of that pi value. So we're going to do this. So that angle is pi minus the related acute, but we know that this angle is negative. So I'm just going to put that outside the bracket. It makes my life a little easier as I calculate it. So pi minus the related acute angle, we actually calculated that before. Oh, no, we didn't. We're good, actually. So we have pi minus 0.927 approximately, which gives us negative 2.214 radians, which I can write without the brackets now that I can kind of work with that. So that's theta 3. Now the next thing is to look at theta 4. So that's this one that goes all the way back here to this terminal arm over here. That's our theta 4 that we're interested in. So theta 4, we can see, is all the way going in the negative direction to pi, and then going a little further by that related acute angle. So we calculate that. So we can see that theta 4 is negative 4.069 radians. So now we have all 4 of our answers. We have theta 1 was 2.214 radians, theta 2 was 4.069 radians, theta 3 was negative 2.214 radians, and theta 4 was negative 4.069 radians. This doesn't always happen where you get the same numbers, like where this number is the same as this number but negative. That does not always happen. It's just because of the 2 quadrants that we happen to be in, quadrants 2 and 3. So that makes me realize we should do one more example so that you can see that those that kind of pattern doesn't always happen. So here's one. So sine of theta is negative 0.8. So this looks a little different than the other ones. I don't have my x, y, and r values as a fraction given to me. I could get that by turning 0.8 into a decimal, or sorry, into a fraction. But there's another way for me to just get a rough sketch, is just to think about, like we talked about at the beginning of this kind of topic here, was that sine is positive in the top quadrants here, and cos is positive on the right-hand side quadrants over here, and we know that tan is positive in the kind of diagonal alternate ones. So since we know that sine is positive in the top half of the Cartesian plane, we know that the 2 terminal arms that we're looking for must be in the bottom. So there and there, somewhere in those 2 quadrants. I don't know where, so I just give a rough kind of sketch in the middle of each, and then I kind of build out of that. So I know that because of this domain restriction, I can go positive once and again to the other terminal arm, and I can go negative once and again to the negative terminal arm. Okay, so I know I'm going to have 4 possibilities that I can work with here. So now I start by using my calculator. So I have sine theta is negative 0.8. I'm going to isolate theta by using the sine inverse, and I'm going to make sure that my calculator is in radian mode as I do that. And I get negative 0.927 approximately. So for this, I need to consider which angle have I been given. What does my calculator spit out for me? So it's a little less than 1 radian in the negative direction. So that feels pretty good about this space right here. So I'm going in the negative direction, and I'm going to a terminal arm that gives me an acute angle going that way. So I feel pretty good about the fact that that's theta 1. Now, I observe that, oh, theta 1 is actually the same thing there as my related acute angle. So I know the related acute angle is this amount as well, just the positive amount. Okay, so we have beta is a related acute, is approximately 0.927. I always try to remember to put my approximately symbol when I know that I have a rounded value. So that means that this related acute angle in here is also beta, 0.927 radians approximately. So I can find the other negative angle really easily. I know that it would go from the initial arm to that terminal arm in the negative direction. So I need to find out how much that is. So theta 2 is going to be a negative angle, and it's as big as pi, because I know pi is over here, minus that related acute angle, but negative. So we have pi minus beta, but negative, so I want to know how much that is, so I evaluate that. So that gives me negative 2.214 radians approximately, so that is theta 2. Okay, so in theta 2 is in red, and theta 1 is in green. Okay, so now I know that I have other angles as well, because I can go in the positive direction, and I know that because my domain is wide enough to let me do that, that now I need to see how much is this angle that goes all the way to that terminal arm, but in the positive direction. So to find that, that's going to be theta 3. So I can see that that's pi, right? I'm going all the way to pi, and then I'm going a little bit past. I'm going the related acute angle past that, so I'm going to add that to pi. And I get 4.069 as my approximate value for theta 3 in blue there. And now I'm looking for that last angle, theta 4, that goes in the positive direction all the way to that other terminal arm there. And now I look for that one. So theta 4. I can see that that's almost all the way around the circle. So it's almost to 2 pi, but the related acute angle is kind of the space between that terminal arm and the end of that 2 pi. So that means I can find that angle by doing 2 pi minus that related acute. And that gives me about 5.354 radians. And again, I do that mental check. Does that seem reasonable? Well, the angle is over here, right? So we know that that's almost all the way around the circle. And so we know all the way around the circle is a little bit more than 6 pi radians, a little bit more than 6 radians, and 5.356 is, shy of that, reasonably so to keep me in that fourth quadrant there. So I have my 4 answers. I have the one that I just found, theta 4, going all the way to that terminal arm in the fourth quadrant. I have theta 3 that goes all the way to the terminal arm in the third quadrant, and those are both positive angles going in the positive direction. Then I have the negative angle that goes to the terminal arm in the fourth quadrant, and the negative angle that goes to the terminal arm in the third quadrant. So I have all 4 answers. Notice that none of the numbers are the same, okay? So the last example that we looked at, they were kind of in pairs of positive, negative. That doesn't always happen. Depends on where your terminal arms are.